Oh, yes. Welcome to Üçgen, the 11th talk of Üçgen algebraic geometry seminar series. And today our guest is Irem Portakal from University of Magdeburg, and she will tell us about rigid toric matrix Schubert varieties.
Yeah, thank you for the invitation, and also thank you for this nice organization. Yeah, I'm going to talk about this long title. So I will first talk about what is a matrix Schubert variety, and it turns out that they are easily defined combinatorially, and then we will really see concretely what they are, also with pictures and so on. And then afterwards, I will say what is a toric matrix Schubert variety with respect to which torus action, and then a little bit about deformation theory and how do we deform these varieties, and whenever their deformations are always trivial, and then try to link between these three worlds, again, with combinatorial tools. So that's my plan for the talk. First of all, the matrix Schubert varieties, then deformation theory, and afterwards, like linking these three worlds. One is the graph theory, and then toric varieties, and then deformations. Okay, some parts of this talk might be a little bit technical, so I will try to give a lot of examples. And the reason that I sometimes give details to the technical structures is to give you a motivation why I did the following thing and so on. All right, so first of all, matrix Schubert varieties. They're always associated to a permutation. We consider pi in permutation, and for each permutation we have a permutation matrix, which we fix this definition. I heard that there are many other definitions for permutation matrix, so let me fix it here. And this is a matrix where n times n matrix, where you put ones on the ith row and jth column whenever you have pi of j is equal to I. And you consider this group action. B minus is the invertible lower triangular n times n matrices. B plus is the invertible upper triangular n times n matrices on the n times n matrices as just m minus m and m plus minus 1. And after that, the formal definition of a matrix Schubert variety is just taking this orbit of the permutation matrix under this nice group action and take the Zariski closure of it, and this is called the matrix Schubert variety of pi. So these, okay, you don't really see so much about the variety here. For example, what is its defining ideal? What is its dimension? You can't really see it right away from the definition. So we are going to understand these objects via combinatorial structures, namely Rothe diagrams. And after that, we are going to observe that these varieties actually always looking like some important and interesting part, y pi, times some affine space. And we will be interested in this part, this interesting part, y pi. So actually, when I say toric matrix Schubert varieties, I mean toric y pi. So I'm just going to discard this affine part, and I will focus on this part for the matrix Schubert varieties. And the toric ones have been classified, the toric y pi's have been classified by Escobar and Messeros about 4 years ago. And we are going to take this classification and translate it to the language of bipartite graphs, because it turns out that, I mean, at least for me, subjectively, it was easier to understand these varieties in terms of bipartite graphs, and it was also intersecting back then with my PhD topic where I was trying to understand the toric varieties arising from bipartite graphs. And it turns out these toric matrix Schubert varieties is a very nice subclass of these toric varieties arising from bipartite graphs. So I'm going to translate this language meaning the Rota diagram, to bipartite graphs, and we'll work on there. So what is a Rota diagram? It is basically a n times n grid and encoding the inversions of your permutation. So here you see this means, and you have whenever you have an inversion, you just color a box in your grid. Example. Here, maybe the easy way to draw a Rota diagram will be, let me give you the permutation here. Pi is 2, 4, 1, 3. How did I just read it so quickly? Is that you put dots whenever you have a 1 in your permutation matrix for this permutation, and you just delete the boxes underneath and to the right, as I did here with the red lines. And the remaining part is basically encoding the inversions of your permutation. And this blue part is my d pi. And I gave two definitions here for the Rota diagram, which will be useful for us to understand the defining ideal of the matrix Schubert variety. The first of it is the essential set. Maybe you saw it also in another context. It just means that you look at all the connected components of your Rota diagram, and you look at the southeast corners of it. So if I go to the first connected component, the southeast corner will be just this one, you know. And for the second connected component of my diagram, this is going to be this is the only box anyways. So these stars are my essential sets. And we also have this dominant part, which is just the connected part attached to this upper northwest corner, basically attached to 1, 1. So this yellow thing is the dominant part. Okay, I will go back to that picture in a minute with an example. But this is important because one more thing that I'm gonna, just one more notation. You have this n times n matrix that, you know, we had the group action on. Let's call this is an M matrix. And you consider this submatrix here, which I denoted by AB, with A rows and B columns. And we are going to consider this rank function, which is denoted as RMAB, which is the rank of this submatrix here, MAB. Okay, now comes the magic, which is the result of Fulton, where he really nicely explained how you can define these varieties, the defining ideal of these varieties. So first of all, the dimension of this variety is just n squared minus the number of inversions, or the number of boxes in your Rota diagram. And it says it can be defined as a scheme by the equations where you have the rank function here, AB. So this is the rank of the submatrix with A rows and B columns, should be smaller than or equal to the submatrix of the permutation matrix pi with A rows and B columns. But only for the boxes, it's enough to look at the essential sets, basically. So this is a very nice result. It's a very concrete result for us to understand the variety. Let's see how we do that for our permutation, for example. So we take the same one for 1, 1, 3. Remember, we had two essential sets. Let me go back. So we had two essential sets. One of them was just 1, 2, this red one. And the other one is just, maybe I write it properly. So here, 1, 2, and 3, 2. Okay, so let me try to apply this theorem, so the full-tone conditions, to understand this, the ideal. If you start with this first essential set, which actually we also remarked that this is in the dominant part. So we need for the first one, the following inequality. So for the generic matrix, rank M should be smaller than or equal to, if you look at the submatrix of the permutation matrix pi, which is going to have no ones. So the, you remember the ones were the dots here in the picture. It's going to have no ones, so the rank should be 0. The rank of the submatrix should be smaller than or equal to 0. That means that we have zeros for this generic matrix in these spots. So in general, also you can maybe realize that whenever you have an essential set in the dominant part, these boxes or like these entries in the matrix should be 0 because there will be no dots in this. So in general, dominant part will look like this. And this will contain no ones here. So the ranks of the all submatrices that we will consider will be always 0. So this was the first essential set. And the second one is 3, 2. Let's go to the example. Oops, sorry. So as I wrote here, for the first essential set, we have zeros coming from this theorem here, from this inequality. And for the second one, we have 3, 2. And this rank should be smaller than 1 because if we again go back, it means that we are looking at this submatrix here of pi, and its rank is just 1. So the rank of this submatrix should be smaller than or equal to 1. That means that here this determinant of this 2 times 2 matrix should vanish. So here we go. We had this ideal of this variety by just using these rank inequalities. This is how we do, and it is very, as you can see, it's very concrete, and you can really, I had the feeling that you can really understand the variety with this theorem. Okay. Am I too fast? Maybe I can stop here if you have any questions.
I have a small question. In the previous page, you drew a picture, a staircase picture that I raised. What is the southeast corner for?
So you will have many, right? Let me maybe.
Or what are, yeah.
Okay, so let's. It's going to look like you have the screw diagram, and you will have a bunch of essential sets, right? For example, this corner, this corner, this corner, this corner, the most southeast ones.
Thank you.
I wanted to ask a question about actually, like, how about the degree? Is there any, I mean, in terms of the combinatorics of the full tone statement?
What do you mean by degrees?
Degree of the variety. Degree.
Oh, well, I don't really go into that. I don't really know if, I don't really know. I didn't really go into that.
Just like in terms of, the number of essential sets, I mean, the cardinality or the dom.
I'm sure there should be a result of it, but it doesn't really come to my mind. I can check it out.
Okay, thanks.
Okay, then I go forward. So as I said, that we have this interesting part of the matrix Schubert variety, the y pi, and this affine space. We can also see it on the rotor diagrams. I'm going to do the same example here. So d pi, we had this diagram, and you see, so we are, as we are imposing the Fulton conditions, we are always interested in this, submatrices depending on the essential set. So basically we are interested in the boxes which are northwest of all these essential sets. So we are also going to take these boxes, which is the northwest boxes of each essential set of pi, because these are the interesting parts, as we saw in the example just a second ago, where we are imposing the Fulton conditions in the submatrices. And next I talked about the how dominant part is basically the encoding the entries, the zero entries in the matrix. So I'm gonna call L pi as the boxes without the northwest boxes without the dominant part. So this is going to be here, for example. And one more thing is that we'll be also interested in these boxes, which is called L prime, defined as northwest boxes without the rotor diagram. So why is this important? Remember, so, okay, since we're not imposing to the boxes which are not northwest of any essential sets, the remaining boxes here, for example, like these ones, are free. So these are the ones giving us this affine space. And we know from the theorem that the dimension of the matrix Schubert variety is n squared minus the number of boxes. So minus, if we consider n squared minus the number of northwest boxes, which is going to be the free ones, this should be the dimension of the interesting part. So it turns out that the dimension of y pi is the number of boxes in this L prime pi. So this is important because when we are looking the complexity of the torus action on this y pi, like if it's toric, for example, then we are going to, of course, need this dimension. Also, we're going to need the dimension of the torus acting on there. And in particular, we have here 10 free boxes for our example, and this variety was 3-dimensional because generated by one binomial. Okay, so this was matrix Schubert varieties. Let me talk about what I mean by a torus action and how I understand it in terms of graphs. We just basically consider the restricted action. So we just restrict this b minus times b plus to the torus. And this is called also in the literature the usual torus action. So on Kasten-Lussig varieties and so on in general. And yeah, Escobar and Mesiros classified this y pi's when they are toric. They said if and only if these L prime consist of disjoint hooks not sharing a row or column. So geometrically just means like a hook in their language means something like this, like with 1 here, and they're not allowing to have another hook here which is crossing this, for example, sharing a row. This is another hook. This is not allowed. And if you remember for the, maybe I said it before, for the torus action, the important part is L of pi for us. So I would like to translate this information from the rotor diagram. Whenever I have a box in L of pi, in the 8th row and the bth column, I'm just going to put an edge for a graph, which I call G pi AB. So this is how I basically take the information from the rotor diagram to graphs to understand the torus action. And maybe I go back to the one picture that I drew. You see, this L of pi is basically responsible of the coordinates of the variety y pi. This is why I'm just considering the boxes coming from L of pi, roughly. Okay, so yeah, this is how I basically translate it. Well, good, but how do I use these graphs to understand the toric varieties then? Maybe I talk about that and then I stop again for a bit. So first I tell you about what is an affine toric variety associated to a graph. So you take a simple graph, and actually I'm taking an undirected graph, and its vertex set as V of G and its edge set as E of G. And we define this edge ring, which is basically that we have here Ti, Tj's whenever I have an Ij edge. And then I write the surjective ring morphism where I have a polynomial ring here, xe's to the edge ring, and xe's go to the Tij whenever Ij is an edge. And if you consider the kernel of this map, this is called an edge ideal. And this is always binomial, actually. And the associated toric variety to the graph G is basically defined as you take your polynomial ring, quotient it out by your edge ideal, and take the spec. And yeah, where of course when you have a toric variety, you have an associated cone, and I will call this cone an edge cone, basically. Example, just let's take the complete connected bipartite graph. Here, as in the picture, we have 4 edges. So we have this polynomial ring and the edge ring as we defined in the previous slide. Then the kernel of this is generated by this binomial. Actually, in general, also the kernel of this map is encoded or can be understood by the primitive even cycles of on your graph. And here we have only one cycle, so we have only one binomial. And the dual cone here, which is associated to our toric variety, is generated by the external rays, these 4 external rays. And you can actually see these are really coming from the edges. For example, for the first one, you have, it's coming from this edge 1, 4. And this one is coming from the edge 1, 3. And this one is coming from the edge 2, 3 and 2, 4. So it's very easy to understand this dual cone in the M space, but it's not straightforward to see directly from the edges to understand what is sigma G, so the dual of this dual cone in the N space for the toric variety. This is going to be another subsection and towards the end of this talk to understand this dual of this cone in terms of graphs. And this will help us to understand, interestingly, the deformations of the toric variety. So let me do the reformulation in terms of graphs. For this example, again, the same one. You remember we had this rotary diagram. And we had this L of pi, which was the part of the diagram providing the information for the torus action. And for each box, I add an edge for my graph. So here you see 2, 1. I didn't change the labels for the matrix. I just put squares and circles here to distinguish that this is a bipartite graph. And you have 2, 1, 2, 2, 3, 1, 3, 2. And this is the graph G pi. And yeah, also we can see the dimension of the toric variety can be just understood like this associated toric variety to the graph is just the number of vertices of your graph minus number of connected components. And in this case, we have 4 vertices, 1 connected component, and it's just 3. And the dimension of y pi is also known by just counting these boxes in L prime pi. So it's also 3. And basically, this is how you find out about the complexity of the torus action on this variety. And we find out this is toric, for example, like this. Or you can also see that this is a hook shape. Okay, so any other questions? Maybe also take a minute.
I am good, thank you.
I guess no questions.
Okay, I just took a sip from my water. Okay. Yeah, so this is it about toric matrix Schubert varieties. And now I just talk about very briefly about deformation theory, what I mean by a deformation. And mostly I will be interested in this part, deformations of toric varieties. So by a deformation, I mean a first order deformation, which means that your base space here is a spec of dual numbers. And then you're considering a nice map, this is a flat morphism, where the zero fiber of this morphism is the variety that you would like to deform. And if this diagram commutes, then you say that this is a deformation of X0. Of course, you can change your base space. What I'm considering here the first order deformations, since I'm interested in the rigidity. And there's this T1 space that I'm going to talk about. Is the set of deformation of X0 over this spec of dual numbers, modular isomorphisms. And a variety called rigid if this T1 space is 0. So this implies actually also that X0 has no non-trivial infinitesimal deformations. This means you can take any other base space S and over an Artin ring. Then any deformation is trivial. That means is an isomorphic to the trivial deformation. So it's like a very big question, and it is in general really not easy to find rigid examples. But for the toric varieties, again, there's a combinatorial way of doing this, which I will be focusing on that. And this is actually very technical, but this will give us the opportunity to understand why I needed to do things that I will explain in section 3. So what are the steps to construct the T1 space for the toric varieties? So this is a, I think 30 years ago, Altman, who is my PhD advisor, did, and he proved that this T1 space is multigraded by the lattice elements of M. So we will be focusing on this homogeneous part of this T1 space. And this homogeneous part can be constructed, again, by using the cones, the associated cones to the toric variety. So let us fix a deformation degree. Basically, it's just a lattice point, R, and he considers the cone here in the N space. So remember, we had this dual edge cone, which was in the M space, and I was saying, okay, we will need to understand the dual of this dual cone. This is the first motivation that this is why I did that. So he considers the cone in the N space. So let me just draw pictures here to explain this technical thing. So let's say that we have such a three-dimensional cone with this 4 external rays, and this is my sigma. And he considers this R is equal to 1, which is basically what he does. Oops, sorry, maybe I have to do this here again. So let's say this is my sigma. And he considers this crosscut of sigma, basically taking this R is equal to 1, which is just the, maybe just draw it. I just take some specific hyperplane and cut this cone. And I got, for example, I can get a compact thing as a crosscut. I can get a polyhedra. I can get an infinity. I can get a cone, anything. So what he does, taking a cone and then considering this crosscut as I did here, and this is going to look like, in our example, something two-dimensional. And he works with this crosscut. He then puts some technical things as explained here. First of all, considers the compact edges of this crosscut. So in the example, we have 4 compact edges. And then for each, so compact edges, and for each two-dimensional compact face, in our case, we have only 1. Let's call this an epsilon. Then they assign the sign vector such that they fit into a cycle along the edges. So what I mean, for example, we can take 1, 1, 1, 1, such that it just fits into a cycle along the edges, compact edges of the compact face. So this is the second motivation why I talk about this, because he is interested in the compact edges, which are the external rays of sigma and can be understood by, and the two-dimensional compact faces of the cone, which are the three-dimensional faces of the cone, roughly. So yeah, this is what he does. And after that, he finds a vector space where we had this sign vectors along the edges. But now we want these T1, T2, T3, T4s also give the give this equation. So T1 like the is a vector plus t2 is a vector plus t3 plus t4 to be 0. All right, so on an example, and we had this complete bipartite graph, 2, 2. And we had this cone, and we can calculate the dual cone as E1, E2, E3 for canonical basis. This is actually a 3-dimensional cone because I'm taking this space as this, just a detail, don't worry about this. And as in the pictures that I just drew, you can take the deformation degree 1, 1, 1 and cut this cone with it. And you will get, so actually this is K22, you will get this as a compact cut. This is cross cut, as written here. So this was the first step. And also for the vector space that he was talking about, you can, here for this example, you can calculate that this is actually just T1, T2, T1, T2. And one more corollary about this technical theory is that if you have a toric variety, which is smooth in codimension 2, then things are easier. Remember you had this crosscut, the compact 2 phase and the crosscut. And they say, okay, this T1 space is contained in this V of R, which was looking like this, quotient out by the same ones. Moreover, it's built by those vectors satisfying the following. If you have an vertex here, let's say a J, if it's a non-lattice common vertex of this edge here, Ti or Dij and Djk, if it's a non-lattice common vertex, then you could directly say that Tij is equal to Tjk in this V of R. So it's very combinatorial, but very technical. But as far as we saw that we are interested in the, so 2-dimensional compact faces in the crosscut, so 3-dimensional faces of our cone, the compact edges, which means the 2-dimensional faces of our cone, and the external rays. So to be able to say something about deformations of toric varieties coming from graphs, we would like to understand, if in terms of graphs, we would like to understand the faces of cones, of this cone in terms of graphs. And yeah, for this example, we see that for this deformation degree, this homogeneous piece is not 0, hence the whole T1 space is not 0. That means that the toric variety is not rigid. So if you find, of course, one deformation degree where you have the homogeneous piece not 0, you can automatically say that the variety is not rigid, and it's very easy to have non-rigid examples. Yeah, as I said before, we need an explicit description of the faces of the edge cone, and which is what we're going to do now. And yeah, are there any questions maybe? Or is anyone there?
We are here, but we don't have I don't have a question. Actually, maybe something about social cohomology, maybe. Like, can you Can you say something
Cohomology?
about the Hochschild cohomology of?
Yeah, there's some work of Mattei Philipp, who did the deformations of toric varieties using Hochschild cohomology. There's a paper of him, if you mean that.
Yeah. So I mean, can you do that combinatorically? Is it what that person?
Yes, yeah. He does also combinatorially. He does also using cones.
Cool. Thank you. I haven't heard the name, but I will watch the video again or ask you to clarify what the name was.
Okay.
Thank you.
Okay, so the last part of this talk is about, so we talked about many things, right? We talked about matrix Schubert varieties, rotor diagrams. We talked about deformation theory, this huge theory, and toric varieties, cones, graphs. And what I would like to do in the end of this talk is to tell you something about the rigidity. So basically classify the rigid toric matrix Schubert varieties in terms of graphs. Hence, afterwards, I can retranslate this back to rotor diagrams. But for that, I need to find this link between graphs, faces, and the deformations, the methods that I just talked about of Altman. And for that, we would be interested in independent sets of graphs. The independent set just means a subset of the vertex set of the graph where you don't have any adjacent vertices. So if you think, for example, just an isolated vertex, this is going to be an independent set. Or you can think the disjoint set of the bipartite graph, which is also going to be an independent set because there are no adjacent vertices. Next, the neighbor set of A here just means all the vertices attached to the vertices in A. So if you're taking A to be just the vertex set 1, neighbor set will be 3 and 4. Since I promised you to find the faces of the cone, we will need a supporting hyperplane. And this is defined as just follows, this HA. Here you have all the elements from the M space where you consider the sum xi's, where these i's are coming from, these indices are coming from A, and these indices are coming from the neighbor set. So if you just think the same example again, you're going to have this supporting hyperplane x1 is equal to x3 plus x4. Then induced subgraph, I don't know, maybe you know all these graph objects, but for the people who never studied in graph theory, maybe induced subgraph just means, you know that as G of X, X is a subset of vertices, vertex set. It just means take these vertices and also take all the edges between them. So if I take 1, 3, 4, it's going to be this subgraph here. And an associated bipartite or subgraph of G to an independent set will be taking this induced subgraph of A union neighbor set of A, which you can see here, and just take also the remaining isolated vertices here. So keep the number of vertices the same as the graph. And here comes the fancy object, the first independent sets. They just mean we are taking two-sided maximal independent sets which means, you know, you have a bipartite graph, you have two sides, U1 and U2, and you have a bunch of edges in between. And two-sided maximal independent set means that you're taking vertices from both sides, from here and here, and it should be maximal. And one-sided independent sets, meaning, as you can guess, just taking vertices from one side and removing exactly one vertex. Plus, we just want this associated graph that I just talked about to have two connected components. And this gives us a one-to-one correspondence between the external rays of sigma g and the first independent sets. Here we have the sporting hyperplane, and this was a dual edge-cone that we knew that it was encoded by the edges of the graph, and take the dual of it, you get the external ray. And yeah, this is how you understand the external rays in terms of graphs. So the first part is done. Let me show you an example. This is again K22. You don't have any two-sided maximal independent sets because this is a complete bipartite graph, and all the first independent sets are isolated vertices. And we are going to now attach this soon to deformations. But the second thing was to understand what are the faces, that at least the two-dimensional and three-dimensional faces of the edge cone. And this is basically done by intersecting these associated subgraphs that I just talked about. This was a notation for the associated subgraphs. So you have one for each external ray of your edge cone. And if you take them, and if you want to know, okay, I have two external rays, for example, I would like to know if they span a two-face of my cone. So you take the graphs and intersect them. And the theorem says, yes, this does, if and only if this intersection has three connected components. So D, for a face of dimension D, you need D plus one connected components. So you can classify, you can understand the faces of your edge cone in terms of graphs like this. Example. So this is how the edge cone looks like for K22. You have the associated external rays here. Remember, this was a funny space. That's why looking three-dimensional. Let's say I would like to understand if E1 and E4 span a two-face here. And I look at the associated graphs, E1 and E4, intersect them. I got this intersection and it has three connected components. So the answer is yes, this span a two-face. So what happens with E1 here and E2, for example? Let's take the associated subgraphs, E1 and E2, intersect them. I get four isolated vertices, so four connected components. And it says, this theorem says that no, they do not span a two-face. So this is how I constructed to understand the deformations of two faces and three faces, deformations of toric varieties via faces. And this was an important link for me. And by using this, basically this face theorem, we can state the following. So you have, first of all, you can say that the toric variety in general, also toric variety associated to a bipartite graph is smooth in codimension 2. And you can also say that this y pi, which was this important part of the matrix Schubert variety, if it's toric, is rigid if and only if the three-dimensional faces of the edge cone, so this was the edge cone, are all simplicial. So simplicial means that they are generated by exactly 3 rays. This is very easy to see, very easy to compute. So you can basically create a lot of rigid examples. The first example will be our example. It's not rigid because you remember this was already a 3-dimensional cone itself, and it had 4 external rays. So this is not simplicial, it's not rigid. And you can go back to the Rothe diagrams, translate this back, and see the rigidity on the Rothe diagrams. And this basically says that if you have a Rothe diagram like this, so let me recall what was this. So these dots are L prime. So they form, is the shape of a hook. And well, this is the whole picture is the picture of NW without the dominant part. So dominant part is somewhere here. And you say the toric y pi is rigid if and only if you don't have, let me go with this first, if you don't have the width of 2 here and here. This is not 2, but this is 2, so it's automatically not rigid actually, this example. And you can also look at other essential sets here. If you have an adjacent essential sets here like this, like a adjacent step, if you will, then this is also not allowed for rigidity. So well, yeah, this was basically what I would like to tell. The aim of this talk was like trying to understand this very complicated and big question of rigidity in terms of very nice and easy objects like Rothe diagrams and graphs. And this talk was also based on my paper with the same title that you can check on arXiv. And these are all the other references that I used. Yeah, thank you so much.
Thank you, Irem, so much for this nice talk. And any questions, comments? Yeah, please, Sage.
So my question is, I see that bipartite graphs play a big role in those like fancy objects, like those one-sided, two-sided independent sets you create. But could you do these things for general graphs? I know you want to create these disjoint things by looking at those I sub G sets. What would happen? Like, is there a particular reason why you have bipartite graphs? And I know bipartite graphs in toric varieties are nice, like they have quadratic Grobner bases, things like that, but like, could you extend the things you did to any graph?
It is, I tried a bit, but it seems, I mean, at least the same way of thinking with this two-sided, I mean, of course, you will not have two-sided things, but like maximally dependent sets and so on, it doesn't seem to work so smoothly in a general graph. Why is it work? Why did I work with them? Maybe I can tell this. This was already, some work was already done by Valencia and Villarreal here. It was this result. They were already working on this, so I tried to understand what they were doing and tried to like basically generalize this to the faces. But in general, it seems to be a hard question to understand the faces of an edge cone coming from any graph. And I, yeah, also like just the deformations of toric varieties coming from any graph, or even for bipartite graphs, like there, at least to my knowledge, there is no classification except the matrix Schubert variety case. So yeah, I don't know if we can maybe also discuss. It would be nice to have a general thing on why. I don't know why it's not working, but as far as I know and tried, it doesn't work.
Okay, thank you.
Ben birkaç soru sorabilir miyim? Merhaba İrem.
Merhaba.
Teşekkürler konuşma için. Önce Selvi'nin bıraktığı yerden bir şey atlamış olabilirim. Basitçe onu sorayım. Her grafa karşılık gelen bir matrix Schubert variety var mı?
Yani toric olanlar için tabii konuşursak evet. Bipartite graph.
Efendim?
Toric olanlar için konuşuyorsak bipartite graphlar için evet.
Peki genelde Selvi'nin sorusunu daha iyi anlamaya çalışıyorum. Herhangi bir graf verdiğimde bu konuşmanın içine oturabilir mi?
Daha genel bir graf verdiğinizde bu konuşmanın tam değil ama bu Kasten-Lustig varyeteleri diye bir grup var. Matrix Schubert variety bunların bir subklası olarak geçiyor. Oradaki torus action'lara baktığımız zaman daha geniş, daha genel graflar görebiliyoruz. Ama Matrix Schubert variety için sadece bipartite grafları düşünmemiz yeterli oluyor.
Yeterli oluyor. Peki. En başta sormam gereken soruyu şimdi soruyorum. Şimdi bir permutation matrix vardı. Onu sağdan soldan üçgen matrislerle çarptık. Daha doğrusu bir action var. O action'a göre bir orbite baktık ve onun Zariski closure'ını aldık. Niye? Nedir bu permutation matrislerin orbitleri? Bu cisim nedir? Nesne.
Nasıl nedir?
Yani niye bununla ilgileniyoruz? Matrix Schubert variety'lerle şu ekranda gördüğümüz.
Yani bu aslında Fulton'un başka bir şey çalışırken bulduğu bir şey benim anladığım kadarıyla. Sanıyorum başta degeneracy lossy gibi bir şey bir paper'ın üzerinden. Yani genel olarak şey söyleyebilirim sadece bu Matrix Schubert varyeteleri full flag manifold içindeki o Schubert varyetelerle de alakalı objeler ama daha combinatorial.
Nasıl alakalı?
Şu şekilde işte mesela bu full flag manifold içindeki Schubert variety'yi düşünürsek şöyle bir Kasten ve Lustig'in bir isomorphism teorisi var. Buradaki yine Schubert varyetesini alıp bunun affine kısımlarına bakıyoruz. Bu opposite Schubert cell oluyor. Şuradaki omega. Bunun burada bir tane işte KL variety diye geçen Kasten-Lustig varyetesi. Bunlar yani Matrix Schubert variety'ler aslında onlar KL variety'lerin bir subklası olarak geçtiği için böyle bir ilişki var. Bir de burada yine bir affine space'imiz var. böyle
İlin,
bir alakaları var. Belki öyle bir ilginç yanı olabilir. Bilmiyorum nasıl cevap verebilirim bu soruya.
yani şöyle çok basit bir şey sormaya çalışıyorum aslında. Mesela lineer cebirsi olarak baktığımızda şöyle bir şey görüyorum ben. Basit lineer cebir. Herhangi bir kare matris verildiğinde row reduction'la yukarıdaki satırların aşağıdakileri etkilemesi elementary operation'larıyla bir üst üçgen matrisi elde ediyorum. Sonra da aşağıdaki satırların yukarıya etkilemesine izin vererek bir basitleştirilmiş matris elde ediyorum. Bu matris permütasyon matrisiymiş. Öyle matrisler